Well, this video is an introduction to some concepts about series. So. Let's first define a series is a sum. Okay. So we're going to be using the summation symbol a lot. I think we talked about this during winter term, using the summation symbol. I runs from 1 to n, and then we'll have these terms a sub I. Okay, and so these are going to be a1, a2, a3, up to a sub n. And we can have an infinite series as well. And so in this case, we start from 1, go up to infinity, and then it just goes on without end. Okay. So the first type of series I want to talk about is what's called a geometric series. And a geometric series, the terms are related by a constant multiplier or a constant ratio, depending on how you want to look at it. And the standard form for a geometric series is the sum as I runs from 1 to n of a1 r to the n minus 1. And so when you put 1 in here, I always use that n in the wrong place. No, that's I. There we go. So we put the 1 in for the I. This is r to the 0 power. So that's our first term is a sub 1. And we call this coefficient here a sub 1 because of that. And you may get geometric series that are not in standard form. And you can always just plug in 1 for the index to find out what the first term is. Okay? Now, if we plug in 2, then this will be a sub 1 times r. Okay? And if we plug in 3, it'll be a1r squared, and so on, up to a1r to the n minus 1 when we plug that n in there. Okay? So let's see. Let's look at an example here. Let's say we have, let's do the sum 1 half I to the I minus 1 as I runs from 1, let's just run it up to 5. Okay? That'll keep it simple. And so again, our first term is a half. The second term is a fourth, and then an eighth, a 16th. Let's see here. Right, and then a 32nd. Okay. Let's see. And so, so what I was talking about in terms of the constant multiplier or constant ratio, that's the value of r. All right? And if you look at it in increasing, if you go from A1 to A2 to A3 to A4 and so on, you can do that by multiplying by that value of r. That's the constant multiplier. If you want to think of it as a constant ratio, then if you did 1/8 to 1/4, then you would get 1/2, which is the value of r. And so a sub n over a sub n minus 1 should in general always be equal to r. Okay? And we can just plug that into the standard form here. A sub n is going to be a1 r to the n minus 1. A sub n minus 1 is a1 r to the n minus 2. And so if we calculate this ratio, those a1s cancel each other out, and this r to the n minus 1 over r to the n minus 2 is equal to r. If you think about it, there are a couple of reasons for this. You can pull out an r from the r to the n minus 1, and then these will just cancel each other. So, in any event, that's a geometric series. And like I said, its sort of defining feature is that idea, the constant ratio, okay, the value of r. Now, if we want to find a sum for a geometric series, let's see. If we've got a finite geometric series, then we've got a terminating value up here for the index that we call n. And we'll call this value, whatever it adds up to, we'll call it s. All right? So here's our s, a1, a1r, a1r squared, all the way up to a1r to the n minus 1. Now let's take this whole thing and we're going to multiply on both sides by r. Okay? And so if we do that, over here we get r times s, and here we get a1r, a1r squared, a1r cubed, dot, 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 a1r to the n. All right, now, why did we do that? Well, here's why. Let's go back to our original sum. There it is. And now we're going to subtract the bottom equation from the top equation. So over here we get s minus r times s. If we subtract all of this stuff here, notice how all of these are going to get canceled out. The only thing that's going to be left is the a1. And over here, that's going to be minus a1 r to the n power. So we factor out the s, and we can factor out the a1 as well, and then divide on both sides by 1 minus r. And so this says for a finite geometric series, the sum will be equal to a1 times 1 minus r to the n over 1 minus r. Okay, now, having made that calculation, what if we're working with an infinite geometric series? Well, if we're working with an infinite geometric series, we could take the limit of this sum as n goes to infinity. Okay? So this will be the limit as n goes to infinity of a1, 1 minus r to the n power over 1 minus r. And what's essentially going to happen here is that the only place where you see the n is right here. So if r is greater than 1, or equal to 1 in fact, if r is greater than 1, this is going to go to infinity. Okay? And it'll be a divergent series. But if r is between 1 and negative 1, right? If the absolute value of r is less than 1, then this piece is going to go to 0. And this will just be a1 over 1 minus r. Okay? So that is the way to calculate a sum for a convergent geometric series. So let's infinite geometric series. So let's write this down. Infinite geometric series. The sum will be a1 over 1 minus r if absolute value r less than 1. Okay. So those are sort of the preliminary ideas here for the finite and infinite geometric series. Let's see. Let's take a look at some of the problems on the handout. They're in 3 sections here. So let's start with the first section, which just says evaluate each sum. So, problem 2, we've got the sum j runs from 1 to 10, 2 to the j plus 2. Okay, so notice that this is not in standard form. If you want to put it into standard form, that's fine. There's nothing wrong with that. But really all we need to know is what is a sub 1? and we can find that out by plugging in 1 for the index j, and this comes out to be 2 to the third power, which is 8. Let's see, the value of n is 10. And what else? Oh, we need the value of r. The value of r in this case is equal to 2. And that'll normally be the base of whatever's being raised to the exponent in the series. Okay, so now we can make this calculation. This will be 8 times 1 minus 2 to the 10th divided by 1 minus 2. And notice that these both come out negative, and so that our final answer should turn out to be positive. And so this works out, if we calculate this to be positive, 8,184. All right, let's see here. Let's look at problem 4. This one is I runs from 1 to 8, 3 times 1/10 to the I minus 1. So this is in the standard form. We can see that A1 should be 3, the value of R is going to be 1/10, and N is going to be equal to 8. And so this sum should be equal to, let's see, A1, 1 minus R to the nth power, and then divided by 1 minus R. Okay, so we can use the calculator for this. I wouldn't be shy about that. Be careful as you're calculating this. You know, if you try to type this in all at once, you really have to watch out for parentheses. Okay, so this should come out to be 10/3 or 3.3 repeating. Okay, let's look at a couple more of these, and then we'll look at those problems in the second section of the handout. Let's see here, problem 6. We've got a sum, j runs from 1 to 6, -3 to the k minus 2 power. All right, so again, this is not in standard form, but we can just plug in a 1 here. -3 to the -1 power is equal to -1/3. So that's A1. R is equal to -3, and N is equal to 6. So our sum here should be -1/3, 1 minus -3 to the 6th power divided by 1 minus -3. And notice that this value of R is negative, and that really kind of changes how this is all going to play out. Our denominator here is going to end up being 4. This will be -1/3 times 1 minus whatever 3 to the 6th power is there. Let's see here. Oh, 729? Is that right? Yeah. Okay. And so this will be negative and this will be negative. That'll make the whole thing positive. And what do we come out with on this one? 182 over 3, which is equal to 60 2/3, or 60.6 repeating. Any one of those forms is fine. All right. Let's see here. Well, let's skip down to the ones on the bottom. These are the infinite geometric series, and these are given as infinite sums. So if we look at problem 10, we've got 2 plus 1 plus a half, and so on. All right. Well, this makes it easy to find A1. A1 is 2. Now, we have to calculate the value of R. We have to look and see what is this constant multiplier, what is the constant ratio. So the ratio here is 1 to 2, or 1/2. You can see it here again. A half to 1 is also a half. Okay. Let's see. And there's no n, right? Because this is an infinite geometric series, and so our sum is just going to be a1 divided by 1 minus r. And so that should add up to 4 if we sum that infinity of terms. All right, let's see here. Problem 12. We start with 25, then 5, then 1. So a1 is equal to 25. And the r here, again, the constant ratio is 5 over 25, which is 1/5. And you can see it again here, 1 over 5. So our r is 1/5. And then the sum should be 25 over 1 minus a fifth. And you can do this on the calculator if you'd like to, which is 125 divided by 4. So is that 31.25 or something? All right. Let's look at a couple more here. Yeah, number 14 is kind of interesting. Here we've got 1 minus a half plus a fourth minus dot, dot, dot. Okay, well, a1 is 1. Now here, our constant ratio is negative 1/2. All right, so our r is negative 1/2. And so that means our sum is going to be a1 over 1 minus negative a half, or 2/3. Okay? So this infinite series, which is an alternating series, the terms bounce back and forth between positive and negative. And let me draw you a picture for what it's going to be doing as it dances around this sum value of 2/3. Let's see here. So here's 1, 1/3, 2/3, 1/2. All right, so after one term, you've got a value of 1. After two terms, 1 minus a half is a half. Plus a fourth is going to give you 3/4. All right, minus an eighth is going to give you 5/8. And so what you're going to see is that this thing is going to bounce back and forth, okay? First greater than, then less than, then greater than less than. The eventual sum of this series, which is going to turn out to be 2/3, this is what happens frequently with an alternating series, okay? All right, let's see here. So that was 14. See, what else do we have here? Let's look at 18. 18 is also kind of interesting. So problem 18, we start out with -2 minus a fourth minus 1 over 32. Now notice this is not alternating. These are all negative numbers. Okay, so a sub 1 is -2. What is the constant ratio? Well, you can calculate this by going -1/4 over -2 and seeing that that is positive 1/8. And you can see the same thing, -1 over 32 over -1/4 is also positive 1/8. So our r value is positive 1/8, and so our sum should be -2 over 1 minus an eighth, which is -16 over 7. And you can get some decimal approximation for that if you'd like. It actually is a repeating decimal, but the sevenths are a little bit tricky with that repeating period. Okay, so that's the second section of the handout. Now, the third section, is about infinite geometric series, but in this case, they're going to be written using summation notation. Let's see here. So, for example, problem 20. And let's see, let's put our standard notation down here. There we go. All right, so problem 20, j equals 1 to infinity, 1/3 to the j minus 1. So this is sort of in standard notation. If you think of a sub 1 as being 1 here, then this is in standard notation. We've got an r equal to 1/3. So this is 1 over 2/3, or 3 over 2. All right, let's see here. Yeah, 22 is kind of interesting. So here we've got a sum from 1 to infinity, 1/3 to the j plus 1. So this is not in standard form, even if you think of this as being a 1 in terms of the coefficient. This is j plus 1, and so this is not standard form. We can find out a1 by plugging in 1 into our formula, and so this is 1/3 squared, which is 1/9. So that's the value for a1, and our r is equal to 1/3. So the sum should be 1/9 over 1 minus 1/3. So what is this? 1/9 times 3 over 2, 1/6. Okay. Let's see. Let's look at a couple more. All right. Problem 24. Also not in standard form. 1 over 2 to the I minus 2. I runs from 1 to infinity. So a sub 1 is 1 over 2 to the 1 minus 2, which is 2. And our constant ratio is essentially 1/2. And you can reason that out a little bit. You can calculate a few terms if you want to. So our sum here is going to be 2 over 1 minus 1/2, which works out to be 4. All right, let's see here. Problem 28. Problem 28, we've got the sum as I runs from 1 to infinity, 3/2 to the I minus 1. So this is, again, sort of in standard form if you think of this coefficient as being a 1. So that says that a1 is going to be 1. Our constant ratio is 3/2. So let me just stop here for a minute and point out our ratio is not less than 1. We can't use this formula. This is divergent, okay? If you start adding these terms up, it's going to keep on getting bigger. It's never going to converge to a particular value. So we'll write divergent. Now, here's the thing. You can make this calculation. If you choose to use this formula, even though this tells you not to, for problem 28, you'll get an answer. Equals -2. That's not correct. This thing's going to go to infinity. If you write down the terms and you start adding them up, you'll see there's no way it's going to add up to be -2. So this formula doesn't work if r is greater than 1 or less than -1. So that's just, it's one of those things you just have to recognize, right? If you go ahead and use the formula, you'll get a wrong answer. The key is to recognize that the formula is not going to work in this problem. because our R value is greater than 1. Okay, so problem 28 is divergent. Well, let's keep going. All right, let's see here. Oh, what else do we want to do? Let's do problem 30. See what we get here. So sum from 1 to infinity, 0.7 to the j minus 1. Okay, so this is another one that's in standard form if you consider that this is a coefficient of 1. And again, you can just plug the 1 in there. Anything to the 0 power will give you 1. Our R value in this case is 0.7. And so this will just be 1 over 1 minus 0.7, which is 3 1/3 or 10/3. So that one's pretty straightforward. Let's see, problem 32. What do we have here? Sum k runs from 1 to infinity. 5 times 1.01 to the k. So in this one, this is not standard form, right? Because this is not k minus 1. So because it turns out that our first term here, when we plug that 1 in there, this will be 5 times 1.01, which is 5.05. And the R value here is what's inside there. All right, it's the base for whatever's being raised to the exponent. But again, notice this is greater than 1. This is another divergent series. Okay? If you start calculating these terms and adding them up, it's going to continue to get larger and larger and larger. It'll never converge around a particular value. All right, so we'll look at just one or two more here, see what else we've got. Let's see, so that was 32. 36 is kind of interesting. So let's take a look at that one. All right, so 36. We've got a sum from 1 to infinity, 0.45 to the I minus 4. Okay, so this is not standard form. We can calculate A1 by plugging in 1 for the index, and that means we need to know what's 0.45 to the minus 3 power. I'll get the calculator out in a minute. Our R is going to be 0.45, and so our sum here is going to be whatever this first term turns out to be over 0.55. So let's see what we get here. 0.45 to the minus 3 power. Yeah, and then we just got to divide that by 0.55. And so this turns out to be approximately 19.95. If you like rational numbers, which I do, but even this one, this is kind of going out on a limb. This is like 160,000 over 8,019. Yeah, so that's why I just kind of said approximately equal to 19.95. All right, so that's 36. 38. We've got j runs from 1 to infinity, 7, negative 3/4 to the j minus 1. So this is standard form. So we've got A1 just equal to 7. Our R in this case is negative, negative 3/4. So let's see, our sum then is going to be 7 over 1 minus negative 3/4. So that's going to be equal to 4, right? Because this is 7 times 4/7, and that'll just be equal to 4, right? You've got the double negative here, because when you're doing 1 minus r, this negative sign comes with the formula, but this negative sign right here comes with the value of r. So that becomes 1 plus 3/4, which is 7/4, and that gives us a sum of 4 for that series. All right, one more. Problem 40. We've got a sum from 1 to infinity, negative 2/5 to the 2k power. All right, well, this is definitely not in standard form. And part of that is because our r in this case is not going to be negative 2/5. If you write down some terms here, I think that we can see that. All right. So let's start writing the terms down. Right. A sub 1 is negative 2/5 squared. A sub 2 is negative 2/5 to the 4th power. A sub 3 negative 2/5 to the 6th power. So this is going to be 4 over 25. This one is going to be 16 over 625. And let's see here, what's the next one? 2 to the 6th power should be 64. And then, let's see here, what do we have? 5 to the 6th power, 15,625. All right. So what's happening here, if you look in the numerator, we're multiplying by 4 every time rather than 2. And in the denominator, you can divide these if you don't see it right away, but in the denominator, we're multiplying by 25 each time. Okay? So 4 over 25 is both A1 and R. All right? Let's see here. Oh, another way that you can think about this is if you take this negative 2/5 to the 2k power, that's negative 2/5 squared raised to the k power, right? When you take a power to a power, you multiply them together. So here is your 4 over 25 to the k power. All right. Having done all that, now we just need to calculate the sum is 4 over 25 over 1 minus 4 over 25. So that's going to be 21 over 25. And what is this going to be? This is going to add up to give you 4 over 21. Okay. Well, I think that's a good introduction to this concept of series. Geometric series are pretty common. They're fairly interesting. I think the next video that I make will be about using polynomial series or what are called power series to represent the transcendental functions, which are sines, cosines, logarithms, exponential functions. And that's I find that to be a really interesting topic because it is essentially how your calculator is programmed. That's how your calculator does most of what it's doing in terms of calculating values for the trigonometric functions, as well as making graphs from those values. So we'll look at that in the next video.